10 is equal to 10 minus 11, right? Mod 11. So 10 is congruent to minus 1. So you got to be careful. We have like, you know, AK minus 1, A1, A0. And I have to put some, like, I guess I need to do some kind of notation, like this is the base 10 representation. I mean, when you start working in different bases, you need some notation. We never have that notation in our everyday ordinary stuff because, you know, but I guess, okay, so this is AK 10 to the K, right? I'll do A2 10 squared plus A1 times 10 plus A0, right? But the thing is, you get like, I can trade my 10 for minus 1 to the K, right? Yeah. Well, so like that's minus A1. So what you get is like singles minus tens plus 100s minus thousands and so forth. For example, to figure out, let's see how this goes, like 121. Is that divisible by 11? Yes. Right. Now how's that go? So this is congruent mod 11 to, what did I just say? 1 minus 2 plus 1. Yeah, 0. Which is 0. So we don't have a remainder. So, but you have to take the alternating sum of the digits, starting with plus for the ones, then minus, like that. Something similar is true for 9. Yeah. See, because 9 is, oh no, 9 is, one, it's not, you know, the -1. Now 8, you get powers of 2. Yeah. Like it gets more complicated. 7, you have to do like powers of 3. So there are all kinds of tricks like that, but. Computer science. Mm-hmm. Now, let's see here. A couple more examples. I wanted to make sure I rounded out this lecture with some examples of modular arithmetic, so we didn't just, you know, prove it. I mean, like, it's important to see examples, right? Excuse me. Calculate the cube of 51 modulo 7. All right, so apparently I'm using the, I like this notation sometimes, because this is right, but 51 is 49 plus 2, right? So that's 2, 2, 2, which of course is 8, which is 1. So to put it in other words, the remainder of 51 cubed divided by 7 is 1. So that's kind of cool. I don't even have it simplified. Like in my notes, I just leave it as 8. What a punk. Sad. Simplify 7 to the 100 power. Yowzers. Modulo 6. All right. So you're like, 7 to the 100 is 7 to the 100, but 7 is congruent to 1 mod 6, so it's just. Yeah. Oh. Oh no, that's correct. Here's what's wrong. Check this out. So try this. So here's a wrong thing. So this is bogus. What I'm writing is bogus, but it is something students will sometimes do if they're not thinking. How did I get to 28?
7 times 4.
I guess this example is like maximally wrong. I'm doing all kinds of like terribly wrong things.
Yeah,
This is
I was very confused where you were going.
this anyway. The point of this is like this is a cautionary tale of many wrong things. So my apologies for writing it. The point is you cannot reduce the exponent mod n. All right.
Oh yeah, but you stated that way back.
Right.
Like 20 minutes ago.
Exactly. All right, so next thing to talk about here is what's a good choice for, I mean, how many things are in Zn, by the way?
We're in Zn.
Yes,
N minus 1 things.
how do you know?
So we typically label the set like that. So we go from 0 to n minus 1.
So you say Zn 0, so my question is, how do you know that that's everything?
Because the number of modular things, like you get, it's not a cyclic grouping, it's a cycle. So like by the time you get to n minus 1, n would actually be the first, the equivalence class is equal to 0.
So you're like 0 bar is equal to n bar, so it goes back where it starts. I think that's a good intuition for why it's everything. Here's another way to think about it. Each one of these corresponds to a possible remainder of an integer divided by n. What are the possible remainders for division by n? 0 to n minus 1.
Yeah, because then you get 0 again.
So that's why there are n equivalence classes, because there are n possible remainders for division by n. And they have to be distinct because this is an equivalence relation, and equivalence classes of distinct elements are distinct equivalence classes. Now, that said, this may not be the best way to look at it, right? So, for example, for Z6, yeah, you could write it as 0, right? Or you could also write it let's see here. I'm trying to remember. So minus, which one's the minus? Minus, this is minus 1 bar, right? And this is minus 2 bar. So then there's 3 bar. For Z7, you could list them as you got 0, plus or minus 1 bar, plus or minus 2 bar, plus or minus 3 bar. Looking at that as the representation of Z mod n is often very labor-saving for calculations. Let me show you what I mean. You're like, well, why does it matter, right?
Yeah, because you're just shifting like number line-wise.
Mm-hmm. So f of x equals to x squared plus 2x plus 3, all right? For x in, let's say, Z5. All right? So we can determine if f has a 0 by explicit calculation modulo 5. All right? So all I got to do is plug in 0 bar, plug in plus or minus 1 bar, plug in plus or minus 2 bar. I mean, to be fair, I should really be putting you know, at some point you get like tired of it and you're just like, fine, no bars, you know. But the point is when you plug in 0, you get 3. All right, plug in plus or minus 1, you get plus or minus 1. I'm already tiring of the bars. Plus or minus 1 bar squared, plus or minus 2 bar, plus 3 bar, which is what? Plus or minus 1 squared, still 1 squared. So 1, looks like that's 0. Is that right? That's wrong. Oh, I'm working what? Mod 5. So this was not 0, this was un. 1, 1, 1, 1, 1. I don't know. I'm regretting this plus minus nonsense here. Like, you can just plug in 0, 1, 2, 3. Excuse me, minus 2, minus 1, 0, 1, and 2. Let's see here. So that's, yeah, like you said, that should be, so this is 4 bar, 4 bar. Yeah. Well, that's, see, this is where it gets kind of icky. So that either goes to the plus, gives you 8 bar, plus 3 bar, right?
That's, 11, which is 1, no, 5, yeah, it should be 1.
So this gives me 11, which is 1, yeah. And this gives me 3 bar. Now, of course, when you look at my notes, you'll notice for minus 2, I have 3. For plus 2, I have 1, as we just found again. In the plus or minus notation, it has its, here it's getting in the way. It would have been simpler just to write. But my larger point is, if this was like a 4th power or something, not taking, 4 to the 4th power and just taking minus 2 or 2 to the 4th power, that's a significant, and this savings gets even bigger as the modulus gets bigger, right? Using sort of a symmetric set of representatives. So, by the way, no 0, right? So this quadratic polynomial has no 0 in Z5. Let's see here. It
is almost 4.
Yeah, I think we're just about there. So I guess I wanted to sort of end with this question. If you want to decide, whether or not an equation has a solution in Z, right? One of the things you might try is seeing if you have a solution in Z mod n. Because if you do have a solution in Z mod n, there's a chance that you have an underlying solution in Z. But if you don't, you might be able to actually prove the non-existence of solutions by looking at, well, anyway, there is, it turns out, an interplay between what are called Diophantian solutions, right, like of Diophantus, versus those integer solutions versus the solutions that you find to equations modulo a particular number. And one of the games that we try to play in here is to understand the interplay between those two worlds. So, I mean, again, this goes back to, this is Gauss. A lot of this is, started by, I mean, I think, again, modular arithmetic is older than Gauss, but certainly Gauss used it very powerfully to solve a multitude of problems. But yes, I think I've gone my allotted time for the day, given my late start time. So, thank you.